thanks for all of the great questions in the first half of today's two lectures. Hopefully we can maintain energy and enthusiasm through to the end of the day. I don't envy you after 2 weeks, the last day. That's a tough gig. Okay, so what we're going to do in this section is we're going to build towards some applications and some other broader connections which Peter sort of alluded to in his lecture. But to do that first, we need to talk about models and a little bit more about covariance functions. And in order to do that, I thought it would be great fun, in sort of tradition of Shakir, is to do the big fat covariance function quiz, which involves 3 questions here. So we'll basically introduce the questions, and then you can talk to your neighbour for 5, 6, 7 minutes or something, and then we'll sort of go back and go through these. So these are sort of questions that are carefully chosen to teach us something about covariance functions and broader Gaussian process toolkit. So this is important to do. So the question is, which of the following result in Gaussian processes? If they do result in a Gaussian process, can you compute the mean and the covariance function associated with that Gaussian process? They are roughly arranged in order of difficulty. So the first one says, if we add 2 GPs, is the result f of x a Gaussian process, and the 2 GPs have covariance function sigma 1 and sigma 2 and 2 0 means. That's the first question. The second question says, let's consider a random linear model. Okay, so this is a linear model, G equals mx plus c. X are the inputs, as before in the first bit of the lecture, but m is going to be drawn from a Gaussian distribution, so we're going to randomly draw the gradient from a Gaussian distribution. And we're also going to randomly draw the intercept c from a Gaussian distribution. Is that a GP? What's its covariance function? What's its mean function? And the final one, this is for the GP aficionados, those people, a few people in the audience trying to work on GPs, so this is a sort of slightly harder one, the random sinusoid models. This says h of x, a function, a random function, is equal to a times the cosine of omega t plus, what's the deliberate state? It should be t here, or it should be x here. Yeah, so is h of x is equal to a cos omega x plus b cos sine omega x, where both a and b are now random coefficients of the sinusoids. So notice that this construction here would generate random sinusoids with, if you can remember your trigonometric identities, is equivalent to drawing an amplitude randomly of the sinusoid and the phase randomly. Uniformly around the circle, basically. Okay, questions clear? Everyone happy? Any clarification questions needed? Great, so chat to your neighbour about it. If you want to talk about it, that's fine. Speculate what's going on, or if you want to crunch the numbers, that's also good. I'll give you 5 minutes. If you want to come and grab me and ask some questions, that's also fine. And yeah, fire away. Okay. Let's give you some time, at least to have a chat to your neighbour or some downtime. Great. Okay, so let's go through these one by one. So question number one. Who thinks it's a GP? Great. Excellent. It's always easy to vote. You see everybody else put their hands up. So you can vote your eyes closed. Okay, anyone want to talk us through, it is indeed a GP, anyone want to talk us through the reasoning and maybe tell us how to compute the meaning of the covariance function? Anyone want to? Yep.
First, I kind of assume that it's like a finite number of points, so
yeah.
So it becomes something with an n-dimensional
right.
zero, like a mean and by and then I guess I have a multivariate quotient, and I have to compute the new quotient that comes out from the sum of two quotients. And since the expected value, I just take the expected value of these two quotients that are added together.
Great, yeah.
And since that's a linear operator, it becomes the expected value of each of them. And those are both the mean, which are both zero.
Great, okay, let me slow you up there for a minute. Yeah, so the idea is let's go back to finite dimensional stuff, which we know things about, which will make sense, and then we can always use the consistency type definition of GPs to get back to the infinite thing. And first of all, you can say let's compute the mean function. So this is the first statistic that we need to compute for the GP. Assuming, as you said, everything is linear and Gaussian, so this is indeed going to be a Gaussian process. You just need to compute the mean and the covariance. So the mean is this thing, and you said the expectation is just distributes like this. And maybe just to be absolutely explicit, I will write down what the expectations are over. So here the expectation is over all of the randomness. So that's F1 and F2. F1 and F2, sorry, that's a bit small. And then here when it distributes, there's no F2 in here, so this is just the expectation of F1, this is just the expectation of F2. And then we know up here that the expectation of F1 is 0, and the expectation of F2 is 0, like I said. So this is indeed equal to 0 plus 0, which is equal to 0. Great. Okay, so the mean function is again 0, as you might have guessed in the construction. Everyone happy with that? Let's do the half bit, let's do the covariance function. Okay, so did you mention the progress on the covariance function? Yeah, great. Talk me through it.
So the variance is equal to the covariance of itself. And then I use this thing that I remember that the covariance between x and y is equal to the expected value of x times y minus the expected value of x times the expected value of y.
Great, yeah.
Right. So the first term then becomes the expected value of f1 transpose times f1.
Something like that?
Yes, plus f2 transpose times f2 inside the first expected value.
Yeah, so yeah, you can just keep up with this. If anyone's not happy, just let me know. So this is the definition of the covariance, right? So I've used a slightly different notation for what you were talking about. You using vectors and matrices, where I'm going to use just the function values and use x to index it, and we just consider the covariance between a point x and x prime. You could use the matrices, that's totally fine, but I'm just going to use the function view. And you said this is the definition of the covariance, right? It's the expected value of x times f of x prime minus the mean of f of x times the mean of f of x prime. And I think what you were about to tell me was because of the line above, this thing in here is equal to 0. Alright, the mean. That's the mean. So we already computed the mean up here, the mean is equal to 0. So this is the object that we're rapidly computing. Everyone keeping up here? Everyone happy? Questions? No, there's some blank looking places, but no questions. Who's confused? Put your hand up. Yeah, a couple of people confused. So, the sort of the high-level argument we're making here is if you take as read the sum of two Gaussian random variables is another Gaussian random variable. This is just a whole pile of Gaussian random variables in this function, and the second is a pile in this one. And so any addition of this guy plus this guy is now addition of two random variables, so this is definitely going to be a Gaussian random variable. Then, in order to characterize it, we just need to compute the mean function and the covariance function. And the mean function is just the expected value of f at any location x. And so we write down what the expected value of f is, and then we substitute it in the definition of f in terms of f1 and f2. The covariance is defined by this equation down here. This is the definition of covariance. It's a bit like the variance. The variance would have the, what's the value of a random variable squared minus the mean squared. Right? This is the definition of the variance of variable sigma of x squared, and we're applying the covariance generalization of that to these two processes. So that's sort of all in inverted commas we've done so far. Great. Okay, so we're almost there. What did you do next?
Well, if you then insert the definition of f, then
great. Yeah. This is a bit long. f1 of x. You will see this. Is this too low? Okay. Plus f2 of x. Just going to delete this bit so I've got a bit more space. Wonky writing. Alright, so we've got this one from this guy. Now we need to put this guy in. So, yeah. And now we've got f1 of x prime plus f2 of x prime. Expected value of that big thing in there. Great. Yeah?
And then, well, I consider them vectors, so it became f1 transpose f1.
Yeah.
Plus f2 transpose f2 plus 2 f1 transpose.
Great, so you're going to multiply out this quadratic in f1, right? So let's do that below, because that's going to give us lots of terms. Good, can I jump to the top so everyone's not training their nets? You happy if I start at the top? Thank you. Okay. I'm going to go through this carefully the first time so that you get the general idea, and we can sort of bring up people who don't know about this side of algebra. And then the next two examples we can go through a bit quicker because they end up looking kind of similar. Okay, so let's expand out this. So we have expected value of f1 of x from here, multiplied by f1 of x prime from that, plus, so the order you said it, you did the two terms like this, and f2 of x prime. And then there are, so that's this guy times this guy, and then there are two cross terms. So they look like the expected value of f1 of x, f2 of x prime, and then plus expected value f1 of x prime, f2 of x. Great. That's just multiplying out the quadratic form. And we're almost there. Hold on, everyone, the same with us so far. What did you notice next?
So that's the fun, that's the definition of the variance. And we have the variance, so we like sigma 1 plus sigma 2.
Great, so this one is sigma 1, x prime. Remember the mean of f1 is 0, so that's equivalent to the covariance, which is this thing here. And similarly for the second process, this is sigma 2. What about these pesky things over here? What about these guys?
Since they both have a first or expected value 0,
0. So the two processes are independent. They're drawn independently from these two Gaussian primes, so the cross terms just go just equal to their means. So we just sum the two covariance functions. Okay, so that's vital. Okay, this just goes through the maths that we just did. So when you get the slides later, you don't need to keep your own notes. But the take-home point is that if we add two functions together and they're drawn from Gaussian processes, we get a new Gaussian process where we just add the means, which in this case is 0, and we add the covariances. And this is really useful, because if you think there's some quantity out there that you're measuring in the world, and it's a sum of independent processes that are combined together to give the observed quantity, then you can write down your prior assumptions about those quantities, and then convert them into one covariance matrix of the thing you observe, just be the sum of the individual components. And then you can use Bayesian inference to pick out those individual quantities afterwards. So Carl Rasmussen in his textbook has a really nice example with CO2, where he sort of looks at CO2 trends over time and pulls out a periodic component and a linear increasing component. We'll do one from the automatic statistician project in a minute. We'll talk about when we sort of automatically pull out functions from data that we compose in various ways. So this gives you a way of composing functions to build sort of structured models of data. Any questions about that? Okay, so there's some nice corollaries of this result with sort of a little extension that you need. A Gaussian process multiplied by a deterministic function is also a Gaussian process. So you can take a Gaussian process and multiply it by an exponential, deterministic exponential, that gives you a Gaussian process, for instance. Derivatives of the Gaussian process. A derivative is a linear operator, and Gaussian processes are closed under linear operations, so that's also a Gaussian process, which is really useful in probabilistic numerics. You might be wanting to put a prior on the result of integration, for instance. Similarly, the integral of a GP is also a GP. It's the area under the curve of a GP integrated up to a particular place. That's just a sum of Gaussian random variables, so the integral itself is a Gaussian random variable. Again, really useful in probabilistic numerics, and Philip Hennig might talk about that when he talks later on in summer school. And finally, the convolution of a Gaussian process by deterministic function is also a GP. So if you filter a GP, if you take a Gaussian process and you pass it through a filter, that still gives you a Gaussian process. In many senses, these are just analogues of the normal results for Gaussian random variables, that the linear combination of Gaussian random variables is a Gaussian random variable, but they become sort of even more powerful in this setting and help you build covariance functions. Great. Any questions about question number one? Yep?
Are there any properties of GPs that are normal when you're Gaussian?
That's a good question. I'm sure there's some, but most of them carry over as red. Yeah, it's a good question. If I think of something, I'll let you know. Great. Anything else before we go to question two? Okay, so question two was the random linear model. Let's go over to this side here. Who thinks it's a GP? Right, getting less certain as we move on. Doesn't feel like a Gaussian process, not sure. This may come down to semantics, this one. So in my book here, it is a Gaussian process. Again, because it's a linear combination of two random variables, which are both Gaussian. So M is a Gaussian random variable, and C is a Gaussian random variable, and you're multiplying the first random variable by x, and the second random variable by the constant 1. So it certainly, in that sense, defines a function where any subset of those function values will have a multivariate Gaussian distribution. What's the mean of this Gaussian process? 0. Great. So again, the mean function as a function of x is just the expected value of g of x, and for almost identical reasons that we talked about over there, this expectation distributes, and these, and these things are both 0 by the definition of these two random variables up here. What do people think for the covariance function? Sigma m squared. Is this what you said? Plus sigma c squared?
Yeah.
That sounds right. Okay, let's just very quickly go through that. So this is important. This is important because, remember, this model is a way of generating random straight lines. Straight lines with a random offset and a random gradient. So if we had a way of generating random straight lines, and we can find a covariance function for it, we just plug it into our GP machinery that we've developed, and we've got a way of doing Bayesian linear regressions, fitting straight lines to it. And then maybe, if our data contain a linear trend and some other stuff, we can add this covariance function to one of the other things using the first result, and we'll be able to have the linear trend modeled by this bit, and the other stuff, maybe the periodic bit modeled by F2. That way. So this is why it's important. It's a way of adding a way of allowing GPs to cope with the linear trend bit of data. So this thing, remember again, just from what we talked about over here, the covariance is defined as the expected value of G of X and of G of X prime. Remember the mean is 0, so we can jump straight to just this expression, hopefully. The mean of G is 0, as we showed the first time, so this is equal to the covariance. And this, then we can substitute in the expression for G. So this is the expected value of mx plus c, mx prime plus c. And again, we can do a really similar trick that we did at the top of that whiteboard, right? We can say there's, let me just do it below because I don't have space. There's the bit involving m. So the expected value of mx times mx prime. There's c hitting c, value c squared. And then there's the cross term, c times mx prime. And then the other way around. And these things are again 0 because the two variables are independent. And this thing is this one, and this thing is this one. So this covariance function, if we plug it into GPs, will give us random straight lines out, or fit straight lines for us in a Bayesian way, with probabilistic inference over the coefficients. So straight line regression is a special case. Any comments or questions about that? Nope. Great. Okay, so again, this is on my slides. You're going to go through this in your spare time. So GPs encompass Bayesian linear regression. Notice this feels a bit strange. This is definitely not a non-parametric model. This had two parameters, M and C, but it's a GP. So not all GPs are non-parametric models. Okay? There are certain covariance functions which correspond to non-parametric models, and we're going to talk about that in just a second. But not all covariance functions imply an underlying non-parametric model here. So non-parametric means infinite number of parameters, really, in this setting. And this definitely doesn't have an infinite number of parameters, it's exactly 2. So there's a slight misnomer when people say GPs are non-parametric models. That's not true. Depends what covariance function you use. Okay, let's do question 3. Question 3 is very similar to the one we've just done. It is a GP. I'll put you out of your misery. And let me just, because I've run out of whiteboard, let me just do it on the slide here. Again, the mean is 0 for exactly the same reasons that the mean was 0 on the blackboard over there, right? The average value of A is 0 and the average value of B is 0, so when you take the expectation, that just drops out and you get average value of the function 0. Yep? Oh, good question. Yes, sorry, typo. This is A and B. Thank you. Yeah, thanks very much. Yes, this is expectation of A and B are these two things. Hang over to the last slide. It's right on the next slide, believe it or not, by some bizarreness. So we substituted in H of X in here, and have A cos omega X, and then X prime on the other side here, exactly the same way as we did before, and exactly the same thing happens as before. The cross terms go, and you just get the expected value of A squared and the expected value of B squared, in exactly the same way we got for the linear regression case, and this gives us this line at the end. Okay? Does anyone remember their compound angle formulae? This is like going back to high school probably, or does anyone know another way of writing that that's neater? Yeah, compound angle formula, it's like this. Cos omega x minus x prime. So remember, the covariance functions have to be even functions, they have to be symmetric. Because my covariance with you is your covariance with me, the covariance matrices are symmetric. So we're bound not to get stuff involving sines coming out, because sines are odd functions. So it had to be a cosine of the difference between the two things. So this is another way of getting periodic structure. It's a slightly different thing from the periodic kernel before, but it's there are multiple ways to get periodic structure from GPs and wants to use this cosine covariance function. One of the reasons why I wanted to flag this example up, why I think it's important, is I could have changed this so I've got a sum of sinusoids here, right? I could have summed over A and B. I could have said, oh, let's h of x equal a sum over k sinusoids with coefficients a, k, cos, and each one can have a different frequency. Like this. So we can have a different frequency in each one of those sinusoids and potentially different variances associated to each pair of coefficients A and B. And that expression looks really like a Fourier series. And in fact, using this way, you can build a connection between Gaussian processes and Fourier series and view inferences to GPs as inference to the terms in a Fourier series. Similarly, you can connect it to Fourier transforms. And that's called Bochner's theorem in the GP literature. And the Bochner's theorem says any stationary covariance function subject to conditions can be written as an integral of these cosine functions, cos omega x minus x prime, weighted by the variance at frequency omega. This is like the power spectral density. So in other words, you can build any stationary covariance function up by summing these cosine basis functions weighted by some variance which depend on omega. This is exactly Fourier transforms. People know about Fourier transforms if you'd like an IEEE background or mathematics background. Many Gaussian process approximation schemes are based on this decomposition, so it's a nice way of connecting. It also connects to random features in the kernel literature as well, where you would sample, you do Monte Carlo sampling of this power spectral density in order to approximate systems by taking random samples of cosines and sines. Yeah, great. Okay. Any questions about that? This is probably the most technical bit, by the way, when we talk about it. Great. Okay, so the sum is we can compose functions by adding them together. We can model periodic structure by summing up cosines, and stationary structure by taking a whole series of cosines, and we can model linear trends by this sort of linear covariance function over here. And in a short while, we're going to talk about how the automatic statistician uses that to fit data. Before we do that, I want to give you one other sort of view on this. So both the cosine example and this example you can think of as a basis function view of GPs, where the basis functions in this case were x and the unity function 1. So we could sort of write this model down as mc vector times phi1 of x and phi2 of x, where this one was just equal to x and this one was equal to the constant function 1. And in the sinusoid case, we chose this to be sine omega x, and so cos omega x and sine omega x. Right. So both of these had this flavor of having coefficients that linearly multiply basis functions. Here's another example of that. Here we're going to take a Gaussian basis function and multiply that by a Gaussian random variable to produce a function down here. To start with, I'm just going to use one Gaussian bump. So the recipe is take one coefficient, one Gaussian coefficient, multiply it by a Gaussian bump. And here's some samples from that function. Okay, so surprisingly enough, it just changes the height of that Gaussian up and down. But I could do that for multiple Gaussians. I could increase my vector here to increase the whole stack of Gaussians. And I can play the same game. Now I have to have a coefficient for each one of these Gaussians, and I sum them all up, multiply them by the coefficients, and it gives you this random function at the bottom. And here I'm doing it with even more Gaussian basis functions. And you might see that this thing looks kind of like what we were looking at in the first lecture. It looks a bit like a squared exponential or exponential quadratic function drawn from exponential quadratic covariance function, and you'd be right. So it turns out if you have infinite numbers of basis functions, these Gaussian basis functions, we get back to the exponentiated quadratic. I would walk you through it, but it's a few lines of algebra. Here we go. this is the result. It comes back exactly to this. So the reason why I'm putting this up is because this and Bochner's theorem really show you the infiniteness of the parameters behind the GPs. Because when we were fitting that RBF kernel, the exponentiation quadratic kernel, we didn't have to interact with any of these guys, right? There are an infinite number of coefficients here that suddenly arisen. And that's what's sort of lurking in the background behind that GP. The way you can think about constructing it is by weighting an infinite number of Gaussian basis functions by individual coefficients. But by the magic of the Gaussian process, we can integrate them all out and deal with this much simpler object of covariance function. So they do have infinite numbers of parameters if you use the right covariance functions. And that makes them really powerful. It means they can adapt to the complexity of the data automatically without running out of parameters. Great. Okay. Any questions about that section on covariance functions? Great. Okay. So we're going to just take a little moment now to talk about some models, and then we're going to deploy them in 3 different applications. Okay. So this is a fun game that I like to play. Many people like to play it. Zubin's built his career on playing this game. We're going to articulate a bunch of probabilistic models, ranging from discriminative models to generative models. And they're going to have functions inside them. They're going to be models which involve functions f. And I'm going to play the game of articulating those models where the mappings, those functions are linear functions. And then consider what happens when we swap neural network mappings into those functions. And then finally, put GPs in. And every example is going to have, every sort of example in this table that we're going to build has a sort of a published instance in it. This is what the field does. It builds tables like these, identifies blank spaces, and then publishes a paper on some data set in some sense. And then people like Zubin stand and give talks unifying these you get a free paper for unifying several of these models together. Okay, so let's start with where we were at the first lecture today on this, which is with regression. So let's imagine we've got an observed input x that's giving rise to observed input x which is giving rise to an output y that may be observed or might be missing if you're doing prediction. And the semantics for reading this directed graph is if you're a root in the directed graph, if you look at the top, there's no arrows coming into you, then you're going to be drawn from a multivariate Gaussian with a zero mean and independent covariance. And then all the other nodes will be drawn conditioned on their parents according to a Gaussian distribution where the function is f of x and the noise is independent on each one of the dimensions. So in this sense it says draw x from a Gaussian distribution and then draw y conditioned on x from a Gaussian distribution which is f of x and then some noise in here. Okay. In the first case, the variables observed, this distribution doesn't make any difference, and this is called linear regression. Right? So the y's is a linear combination of the x's with the function just linearly transformed into this matrix W. Okay. We're happy with that to start with. If you changed the output distribution so that it was a Bernoulli of a softmax, something that Shakir flagged up this morning, this would be called logistic regression, would be a classification problem. Great. Okay, so now let's move to the situation where x isn't observed, it's random, it's drawn from this Gaussian distribution. If we've got a linear mapping from x to y, do you know what this model is called? So generate x according to a multivariate Gaussian, zero mean independent identity covariance, and then draw y as a linear combination plus noise. Familiar to anyone? Sorry? So what's the name of the model? Let me write up to the model. The model is p of x is equal to a Gaussian in x with a mean 0 and a covariance identity, and then p of y given x is equal to a Gaussian in y with a mean which is a linear transformation of x, and then isotropic noise in the output. Yeah? Factor analysis. Yeah, there's factor analysis. You all heard of this? Shakir mentioned it in his talk. Factor analysis. or it's also called probabilistic PCA, because it recovers the PCA subspace when the dimensionality of X is smaller than the dimensionality of Y. Yeah, if you don't know about this, it's worth reading about it. It's like a fundamental building block of any probabilistic models, like the Gaussian state space models and so on and so forth. Yeah, so this is called factor analysis. This thing does dimensionality reduction. If the dimensionality of X is smaller than the dimensionality of Y, or it identifies important factors of variability in the data. So psychologists use factor analysis for many years to process data and to pick out sort of meaningful components from data. Admittedly, I'm in a linear model, so it's not super powerful, but it can help summarize quite large data sets. So another structure we could use is just conditionally generate each y based on the previous y. This is called a Gaussian autoregressive or a Markov model. And the final sort of selection of models that I'm going to put up, in a minute we're going to be looking at the neural network variance and the Gaussian process variance. This variant takes an autoregressive structure for x, where each x is generated from the previous one by a Gaussian distribution with a mean, it's a linear combination of the previous ones, and then generates y's through a linear combination of the x's plus Gaussian noise. This is called a linear Gaussian state space model. This is the model behind the Kalman filter. The Kalman filter is doing inference, online inference in this model. Okay, so people have taken each one of those models and they have changed the linear mapping and they made it into a neural network mapping. So in the first instance, this would be called just neural network regression or neural network classification, depending on whether you have discrete outputs or continuous outputs. The instance where we make this mapping a neural network, pass X through a neural network and add Gaussian noise, is called the variational autoencoder, or an instance of a deep generative model. I personally would steer away from using this term, the variational autoencoder. That's more a term that should be used for inference. Variational autoencoder is really about the inference procedure which you use to train the model, although it's become synonymous with exactly this model. But it would be great if we could push back on that and change the terminology, again in Shakir's spirit of accentuating model and inference. So maybe deep generative model is a more appropriate term. These sort of style structures are neural autoregressive density estimation models, which have become really popular for modeling things like speech in WaveNet and pixel CNNs, things like that, are also in this sort of family of doing things. And there are various instances of recurrent neural network linked variable models, NGO, Oliver, people like that. But of course, you don't need to use neural networks, you could use Gaussian processes. So you could replace each one of these functions with a Gaussian process, so this is a whole another slew of publications. So we've already met Gaussian process regression through what we've been looking at so far. Gaussian process for classification is simple to do. You just take what we did for Gaussian process regression and you pass it through a logistic function on the top to get binary Gaussian process logistic regression. If you take this model and replace this mapping with a function drawn from a Gaussian process, you get what's called the Gaussian process latent variable model, a way of doing dimensionality reduction which uses a Gaussian process mapping from the latent variables to the observed variables. Gaussian process autoregressive models are sort of popular in control, and these things at the bottom are called Gaussian process state space models, where every edge on here has a Gaussian process attached to it. So the point I wanted to make here is essentially whenever you've got a nonlinear function, it's up for grabs for replacing it with a Gaussian process. We'll talk about reasons why you may or may not want to do that in a slide or so's time. But rest assured, every one of these linear models and nearly every one of these neural network models has a Gaussian process analog out there if you can find the right paper, essentially. And they're all useful for different things. Okay, does that make sense? I think these pictures where you figure out relationships between different models are super important and somewhat lost in the current community. So if you do have questions about this at the end, it would be great to talk to you you about it. Think about reducing these on a grander scale, perhaps. Good. Okay. Yep.
So on the last call on modeling two models, are we talking that the Y's themselves are now infinite dimensional, or is that?
No, it's just the functions. It's just the functions mapping. So let me just write down the generative process for, say, the bottom one. Where's the other thing? Yeah, where is it? Yeah, so the bottom model, you would generate data from it in the following way. You would generate F from a Gaussian process. So you draw that in your mind. You generate x1 from a Gaussian distribution. You can now generate x2 given x1 and f by just taking f of x1 plus noise. So you pass it through this Gaussian process mapping. And you do that every time step. And then you can generate y1 given, really yt given xt, and another nonlinear function you've drawn. You also have to draw g. So y is just generated by taking g of xt plus noise. So it's the functions which are infinite dimensional, the x's and y's are all just finite dimensional. Yep, question?
The classification is y given x, that's small Gaussian process, or is it passed through nonlinearity?
Yeah, that's no longer a Gaussian process. So this would be drawn from a Gaussian process, and then you have to squish it through the softmax function and the Bernoulli likelihood. And what you get out is definitely not a Gaussian process, again. So apart from this case, all of the rest of them require approximation schemes. They're analytically intractable in the sense that the thing you get out is not a Gaussian process and you can't compute the statistics of it. So the last lecture that I'll give tomorrow will be how to handle those sorts of nonlinearities. So Gaussian processes in general are special. Gaussian process regression is special with Gaussian noise. On small numbers of data points you can do everything analytically. But even there you need approximation methods for big data sets. Yep.
Under what conditions do you, as a general rule of thumb, use the Gaussian process calculation? Is it just composition?
Great, okay. What are Gaussian processes good for, and what are they not good for? I think that's probably the essence of your question. So here is a non-exhaustive list of when you should use TPs and maybe when you shouldn't use Gaussian processes. So things that they're good at. These conditions apply to any of the modeling, any of the areas where you might want to apply one of the models on the previous slide. Okay, so you've got your application area, you figured out roughly what class of model you need. Maybe you need like a length variable model, which is going to do dimensionality reduction. Should I use a linear model? Should I use a neural network? Or should I use a GP? Well, these are some sort of strengths that you can identify, and if these are key in your application, you might want to use a GP. And if it has one of these weaknesses, then probably you don't want to use a GP. So the first thing is, if you want to do interpretable machine learning, it's often easy to interpret the structure that the Gaussian process has learned, because covariance functions contain easy to explain high-level properties of functions. These things like differentiability, periodicity, stationarity, so on and so forth. So for things in like the regression context, it's relatively easy to build interpretable systems around Gaussian processes, although you'd be limited to identifying second-order statistical structure in your data. Point number 2, if you need super data efficient stuff, like you have very small numbers of data points and you want to make the most of that data, so you're willing to spend a lot of compute on a relatively small amount of data, Gaussian processes are quite good. The reason is, firstly, they're non-parametric, so they could potentially model quite rich and complicated structure, but at the same time, they're applying Bayesian inference under the hood, and that means you have lots of flexibility, but at the same time, you avoid overfitting. You have lots of flexibility from having an infinite number of parameters, you avoid overfitting because you're using Bayesian inference. So in a minute, we'll look at Pilco, a reinforcement learning algorithm, which is really good at doing data-efficient reinforcement learning. Second, or third sort of fundamental thing is decision making. If the end goal, I mean, usually the end goal of machine learning algorithm is a decision, and one of the things which sets Bayesian methods, and in particular GP methods, apart is that they often have well-calibrated uncertainties, at least compared to the competition. So by that it means it knows when it doesn't know. It will have high error bars when it doesn't know what's going on. And that's super important in decision making. If you're trying to design a self-driving car and it says there are no pedestrians in the road, you need to know how certain you are about that prediction before you choose your next action. Right? So for decision making, you definitely need uncertainties. And that is one thing where Gaussian processes are good at doing that. So that fits in with the Pilco example you can see in there. Another really important thing is they're very useful in automated machine learning, which includes probabilistic numerics, things like Bayesian optimization and Bayesian quadrature. Again, you'll touch on later on in the course. This is because, at least for regression and classification, the implementations of these methods are now super rock solid, so they can easily be deployed as the inner loop of an algorithm, and they're not going to fall apart, and they're going to be reliable for you. And they often don't involve a long iterative process to train them in certain circumstances. And so it's relatively easy to use them inside the hood of something which is maybe doing optimization for you in Bayesian or computing integrals for you in terms of Bayesian quadrature. So this is sort of thing is sort of perhaps underappreciated, and has a slightly different flavour. All of these properties are perhaps a slightly different flavour from what you want from something to do with machine intelligence or machine perception, like in traditional AI problems. Weaknesses. Okay, so here's the rub. Large number of data points are definitely a weakness. If your data set is 1 million data points or larger, it's going to be hard to deploy Gaussian processes unless there is special structure, either in the inputs, maybe they might be regularly sampled, or in the covariance functions that you're picking. Maybe the covariance function is separable or something like that. Unless you have that special structure, you're going to be inverting a really big matrix, and it will take you a really, really long time. So large number of data points is bad. Also, high-dimensional input spaces are tough as well. And in general, if you have of order 1,000 inputs or more, you probably don't use a Gaussian process. So you'll need to compute the covariance matrix. And the covariance matrix involves a sum, computing distances effectively, and those distances are harder to compute as the size of the space grows. And so the actual compute required to compute the covariance matrix can just sink you before you've even done any processing on it, because you've got to compute all these pairwise distances. Now maybe you can use randomized algorithms like Shakir pointed to, or some other approximation methods, but if you're not doing that, you're going to be limited to these relatively small input spaces. And in my opinion, Gaussian processes are not that useful for modeling images or modeling speech waveforms or things like that. They're much better suited to relatively small problems where you want to well encapsulate uncertainty and maybe medium-sized regression classification problems, things like that, or learn small number of data points. Maybe the combination of both neural networks and Gaussian processes, which a bunch of people are working on, will sort of get the best of both worlds, but that's sort of roughly where Gaussian processes are positioned at the moment. Does this answer your question? Yep, great. Any other questions about deployment? We look at a few examples now, a few example applications. Good, okay. Alright, so this is a plug for Emma, I guess who's probably in the audience somewhere. So Emma works on this really cool project called the Automatic Statistician. Oh, right, there you are. I'm embarrassing in front of everyone. Which is aimed at doing essentially automatic machine learning. Essentially, she wants to put you all out of a job. That's her main goal. So the idea is you will rock up with your data set. They have a really nice website, which maybe some demos will be going live soon. You can upload your data set to it, and it will perform automatic statistical analysis of your data. So here is an airline data set. This is an example from a paper with Dave Duvino and Zubin Garamani and Roger Gross and Josh Tenenbaum. It contains airline passenger numbers through the years. You can see the number of passengers is growing up. There's a periodic cycle as you go from winter to summer and special holidays and things. Lots of people travel. So that's sort of the structure of the data. You upload it to the website, the idea is going to be, and the website processes your data, fits a model, and then returns a report to you. And here is the report that was generated from the airline data. It says, the structure search algorithm has automatically identified 4 additive components in your data. Excuse me. first one is a linearly increasing function for increasing passenger numbers through the years, an approximately periodic function with a period of 1 year. So it knew what the units were on this axis, and so it could figure out what the period was in the units of the input distribution. 1 year because things are happening through the year, summer, winter, and seasons, and things like that. There is a smoothly varying function, and there is also uncorrelated noise with linearly increasing standard deviation. So this is like the discrepancy between the model and the actual observed data, and that's the model's getting worse over time, sort of relatively, so the standard deviation is closing over time. How is this done? Well, it's all done by Gaussian processes. So each one of these is an F. We're going to sum up sort of 4, or I put 5 for some reason, 4 additive components here. We know that if you're going to pick out 4 GPs, underlying GPs from data, you just sum up the covariance functions. So there is a search going on in the background of this algorithm, which is fitting different Gaussian process models with different numbers of components, and it's scoring those models in various different ways. And then it comes back with what it thinks is the best fit, and then it can unpack the covariance function structure that it's learned automatically from data and convert it into plain text so that a non-expert in Gaussian processes can understand what's going on. So the linearly increasing function here was just our friend, question number 2 over here. So it picked out that this was a sensible component in the data. It then composed that. It found that the next thing it needed to compose it with was this weird covariance function. It's swapping in lots of covariance functions to see which one model's the best, and it's sort of using a grammar of covariance functions here. This one is the multiplication of a squared exponential with this periodic covariance function. If you multiply 2 covariance functions, you get a valid covariance function. So the periodic thing here, this is modeling the seasonal structure, and omega is the thing which has a time period of 1 year, angular frequency 2 pi times 1 year. The squared exponential just tells you that it's not perfectly periodic. We don't get exactly the same pattern every single year, and this allows it to sort of drift around a bit between each year. Here's the smooth function. This is sort of, again, the discrepancy of the model over time and the component from the observation noise. And the report, yeah, sorry.
Which part on the second point model the approximately linear?
Approximately periodic split?
On the second point.
This one?
On the second point, there's a part called linearly increasing geometry.
Oh, that's a good point. Yeah, so I sort of obfuscated that. Inside the squared exponential, there was the parameter, the vertical length scale. And the vertical length scale is depending on the input space here. Yeah. Yeah, good question. Yeah, I haven't put everything on there. I'm not sure I've got 5 components here as well, which is another discrepancy in the slide, but there we go. So the report's even better than this. You can then go and unpack, down the report, it will unpack each of these components. So here is the linearly increasing component, passenger numbers. And here is the periodic bit, the approximately periodic bit, with the increasing variance. And here's the sum of those 2 components. And you can figure out what the discrepancy is between the sum of the 2 components and the other components, so the other components aren't modeling too much. So the point I'm making here is that the GP framework is great in this situation, right? It's interpretable, you can convert it to text, it's automatable, it's running really robustly in the background. You know, this is one of the things it's good for. It's not, you're not going to upload an image, it's not described what's in the image. It's going to be much more suited to these sort of low-dimensional regression problems. Any questions about that application? I'm sure Emma will be able to fill you in on any details. Great. Okay, so here's a second really cool deployment of Gaussian processes. This is from Mark Dijsselroth and Carl Rasmussen. So the idea is let's do really data-efficient control for robotics, reinforcement learning for robotics. So here is a very simple system, robotic system. I'll show you a video in a minute. Hopefully I'll get that to work. So here, this is called the cart pole swing-up problem. There is a pendulum here attached to a movable chassis on the cassette on this track. The cassette can either move to the left or can move to the right. It can either apply a force to the right or a force to the left. And what it's got to figure out how to do is to swing up the pendulum and keep it stabilized. And ideally, it's going to be told to stabilize the pendulum somewhere near this red cross, somewhere above this line here, and then we're given a reward associated with how much of the trial did it get that pendulum close to that red cross. And this is doing this in real hardware. Okay? This is not a simulator, this is real hardware with noisy measurements. The sensors get to sort of feed back to the system where it is in the track and what the angle is of this swing up. So we can compute the reward at the end of the trial, and we can sort of learn how to swing this thing up. So here's how the sort of algorithm's going to work. Initially, it's going to apply a random policy. So a policy is a mapping from the current state to an action. It's going to apply a random policy to start with, and it's going to jiggle the pendulum around and collect some data. It's going to do nothing. And then at the end of the trial, we'll stop, and we're going to fit a GP dynamics model, like the autoregressive star model we looked at, to that relatively small number of data points from the system. Doesn't know anything about the system physics to start with at all. Just going to fit those using a time series Gaussian process model. It's then going to perform rollouts in this synthetic model for the system. So it can roll out lots of synthetic samples from what it now thinks the system's going to do, and it can apply its current policy in those synthetic scenarios. And it can improve its policy in the synthetic scenario so it's doing better just based on the outputs of the model. And then it can apply that policy and acquire new real data from the physical world again. And then it can iterate through and through. So let's see, where's video running? Okay, so here we go. This is trial one, random policy. Not so great at doing pendulum swing up. It hasn't learned what's going on. Then it's going to fit its GP model. Right, now go figure out a bit more about what the dynamics are doing, and I can improve my policy for a bit. Now it's learned to move to the right. Well, first off, it just moved to the left. Now it's moving to the right. It gets put back in the starting position again. It uses the data it collected to update its policy model, does the rollouts, updates its policy, and now it can apply its policy to the new trial. So it's swinging up a bit further now. It's not going to the edges of the track like it was doing before. So is that 3 trials? We should keep track of the trials here. So back into its start position. Good intermediate state, right? That's a lot higher reward than what it was getting before, and the music at the same time. But now, it's for the first time, it's visited that state at the top. Before, it never visited that part of the state space, so it really had no idea what was going on. So now, it's pretty good, right? It's now not spinning around wildly. It's getting up there. It's not quite managing to stabilize it at the top. But now it can start to develop its policy a bit better around that vertical position. Oh, yeah, so it's almost got it. I forget how many trials, but maybe 8 or something. 6? 6, alright, somebody's counting. It's good. Now it's stabilized, which is really good. So it's a 2-second trial, so it will come down after 2 seconds. So this is a relatively low-dimensional problem, which brings GPs into the game. It's super data efficient. This is sort of the opposite of what model-free reinforcement learning methods would be doing, right? Which would be using huge numbers of trials to learn these dynamics from data. And at the end, the solution is pretty robust and pretty stable, and we've got a model for what's going on in the background as well. I think it's a pretty impressive demo, although not on the most sexy piece of hardware. This is like second-year undergraduate rig, I think. Great. Okay. Good. Okay, so that's application number 2. So data efficient, decision making, reinforcement learning, very, very nice. I'm going to talk for the last application about deep Gaussian processes, which are sort of a personal favourite of mine. I think these are sort of the state-of-the-art method at the moment for doing sort of medium-sized regression problems, and they fix some of the problems, some of the awkward problems of GPs by essentially allowing you to do non-parametric kernel design. So this is sort of a different way. The automatic physician had this sort of compositional way of learning kernels. This is a different way of learning kernels and covariance functions in a non-parametric way. Okay, so let's sort of describe how this happens. And in a sense, this is sort of the Gaussian process analog to a deep neural network. So it will be a multi-layer version of a GP. So before we had a Gaussian process regression problem that took generated y of x by just taking a Gaussian process function and adding noise. This was some underlying function for some input x, and this was our Gaussian process prime. Now let's do the following. Let's compose some Gaussian processes just like we compose multiple layers of neural nets. So rather than letting f act on x directly, let's pass x through a nonlinearity g that was also drawn from a Gaussian process. Okay? So we're going to do f of g of x, just like we would do the output of a multi-layer perceptron is a function of a function of a function of a function of the inputs. All those functions now be replaced by Gaussian processes. So here's a typical draw from a G, and here's what the composition of those two kernels looks like for a one-dimensional example. Let's see if we can understand it a bit. So notice that in this region of the input space, the first function doesn't change very much. So this entire region just gets mapped to this sort of relatively small region in Z space, the sort of the intermediate representation. And so as I sweep the input across here, I sweep across only one sort of cycle, one length scale of the top layer Gaussian process of function f of z. And so in this region of the input space, our output changes relatively slowly. In the middle here, this function had a much higher gradient. And so when I move the input through this region here, I sweep through quite a large region of the top layer Gaussian process. And so the length scale ends up being much smaller, much wigglier. And so through this composition of two Gaussian processes, we have a method for controlling the length scale in different parts of the space in different ways. And by learning these two functions, we can do sort of non-parametric warping of the inputs, if you like, or discovering of spatially varying length scales. So in a sense, this is going to do automatic non-parametric covariance functional kernel design. By adjusting this function, we end up sort of automatically figuring out what's the best way to warp our data, such that the top layer GP can do really good predictions for our data. You have to do a lot of nifty approximate inference to get this to work correctly, although some of the methods in the lectures tomorrow will be sort of applicable. So here's a quick comparison. I'm not going to lay this, I want to get onto the neural network stuff at the end. This is a comparison to sort of standard neural networks on a bunch, maybe 10 different problems, regression problems, and this is held at log likelihood along the side. And I'm going to show you how two different flavors of neural networks, sort of state-of-the-art neural networks, doing these regression problems, and I compare them to Gaussian processes and to deep Gaussian processes in I showed you in the last slide. So notice that many of these problems are kind of small dimensional. This was 16 input dimensional and 10,000 data points. This one at the end was 500,000 data points and roughly 100 dimensional input spaces. So medium dimensional, not high dimensional, relatively large size, in the order of 500,000 data points. So this is the best form of deterministic Bayesian neural network. So the best deterministic neural network. This is the best form for sampling. This is using MCMC methods. This is Gaussian processes. This is maybe our first interesting result. Notice that Gaussian processes on these sorts of problems are really competitive with neural networks. In some of the data sets, not so much, but in some they're doing really, really well. Again, there's this transition as we get to higher dimensional stuff and large numbers of data points, as the GPs will fall away and the neural networks will pick up. And here's deep Gaussian processes. They're all doing better than the corresponding GPs, and in many instances they're doing better than neural networks. So, my advice for me to you would be, if you care about well-calibrated uncertainty estimates, and you're doing sort of medium to small-size regression problems, DGPs are the way forward. There's a question out there.
with a large contents around
This one? Yeah, so the Boston housing data set, if you've used it, the variability to do different splits of the data in Boston housing is massive. So if your algorithm works well on Boston housing, remain skeptical and try it on other data sets or run lots and lots of splits to make sure that it isn't just due to luck. Yeah. So no, it's a method that's better than optimizing the parameters. It's using variational inference, and it's actually the best one. So we compared to optimizing the parameters, regularizing the parameters using map, using dropout, and pick the best of a whole slew of actual deterministic methods. So yeah, just early stopping, for instance, as well. Do you have a question? This is just three GPs. Yeah, so it depends, 2 hidden layers. Not super deep. Question?
So if you stack GPs inside other GPs, do you lose the
You do, so yeah, you have to use approximate inference and you have to use certain tricks to get that to work. Yeah, so it's not as tractable as an individual Gaussian process.
I would only use it for
You can use it for the original papers are run unsupervised, but I think, yeah, for the minute, I'd say use it for supervised learning. That's the best bet of getting this to work on. Yep. Great, okay, so I have 15 minutes left. I want to talk about some final connections, one of which, this first one has sort of been known for a while, but I think it's really interesting, and there's been some really interesting recent work in this area, so it's super topical, and maybe sheds some interesting light on what's going on in neural networks. So here is a multi-layer perceptron with inputs X, activations, which are just a linear transform of the inputs, which you then apply pointwise nonlinearities to, like a ReLU or a Tench or a soft plus, whatever you want to put in here, and then you linearly combine those hidden units in order to get an output F. This defines a normal multi-layer perceptron, in this case with one hidden layer. Right? This is exactly sort of a regular single hidden layer neural network. Let's put priors on these parameters, much like we put the priors on our linear regression example over here. We put priors on the output weights of the neural network and on the input weights, and let them be Gaussian with some variance. Variance has been sigma v squared on the output and sigma omega squared on the input, and we're going to scale this variance by d to make sure that the variance of the output doesn't get too big as we're going to think about making this hidden layer wider and wider and wider. And we don't want that to increase the scale of the output by adding more and more and more contributions. So we're going to scale down the weights, the variance of the weights accordingly, just to control the variance. If I make the hidden layer infinite, and I take the infinite limit, does anyone guess what we get out? A Gaussian process. So this generates a Gaussian process. Essentially, what Radford and Neal showed in 1996 was that the central limit theorem kicks in here. If you look at this variable here, it's a sum of independent random variables, where the randomness is coming from these weights and the weights down here. And Radford showed for certain activation functions, the central limit theorem kicks in, and you end up with a Gaussian process coming out the back end. So you can think of a GP as a neural network with an infinite dimensional hidden layer. Here's something sort of even more interesting, I think, which I think Radford knew, but he didn't prove, which is if you take the multi-layer perceptron, so now multiple hidden layers, and you put priors on all the weights, input, output, and intermediate ones, and you take all of the hidden layers to infinity, that also gives you a Gaussian process. So if you make your neural network big enough, and you're in MLP land, and you have these sort of Gaussian priors, then you end up getting that Gaussian process. That's interesting for a couple of reasons. Firstly, initialization schemes. So you might have seen sort of like Xavier initialization, the various ways of initializing before you do optimization in your network of weights. And you have to initialize the weights so that you're not saturating in on linearities or you're in sort of reasonable parts of the ReLU function. And it turns out those rules for initialization are to follow essentially this recipe for sampling your initial weights. You sample them from Gaussians and you scale the variances appropriately. and that stops the output blowing up. So this tells us sort of something about how we initialize neural networks. We initialize them to be Gaussian processes. That's the current recipe, and then we optimize from that point. The second interesting thing is people then said, well, let's take the Gaussian processes, the neural networks that we apply to things like MNIST, figure out what the appropriate infinite limit Gaussian process is, and then fit that to MNIST and see how well it does. And the answer is that the GP does better than the MLP. So there's something weird going on here that we don't really understand at the moment, because normally the justification for why multi-layer perceptrons are working well is that they're doing feature extraction, and they're learning a hierarchical representation of digits and strokes and things like that. And Gaussian processes are a flat representation, right? There's no hierarchy learned, it's just a covariance function. So the fact that the Gaussian process is outperforming the MLP means there's something we don't really understand about the MLP learned structure, which is kind of odd. The other thing that people started to do recently is apply similar ideas to ResNets or to CNNs in general, and consider what happens if you make the number of features very large. And similarly, if you make the number of features infinite, you can also get back to a Gaussian process. And Gaussian process is generated in those ways, and that's sort of the state-of-the-art method for doing large-scale classification and regression on image data, if that's something you want to do. So there's some interesting theory there. I think this is interesting moving forward because it sort of points to a direction where maybe Gaussian processes could be relevant to large-scale image processing problems, and it raises some questions about why are neural networks working. Maybe ConvNets are learning feature-based representations, which are good, but maybe not MLPs. So it looks like the MLPs are being dominated by Gaussian processes, at least on data sets like MNIST. You can take that with a pinch of salt. But these are sort of interesting things that will be explored by the field. The other interesting thing is that the central limit theorem kicks in quite quickly. So you don't need that many hidden units. You know, in some situations, order of 50 or 100 before the CLT kicks in, and it ends up looking identically to a Gaussian process, which is perhaps sobering. Okay, so a few last comments on Gaussian processes in disguise. So neural networks that are very wide are Gaussian processes in disguise, as are CNNs with many features. Linear in the parameters models, the talks we talked about over here, and in the RBF example, are Gaussian processes, like Bayesian linear regression. Linear Gaussian state space models, aka the Kalman filter, that's also a Gaussian process. It defines a Gaussian process, a big multivariate joint Gaussian distribution over observations and the latent state, which have a covariance function attached. As we talked about in the last lecture, linear stochastic differential equations are also Gaussian processes. And these other methods like kriging, splines, moving average processes, even time frequency analysis, could all be interpreted as essentially doing inference in Gaussian process models. So they are sort of all over the place as in disguise, although they may have different names. That's one of the reasons why I think they're important. Okay, I'm going to wrap up here. Here are some references on different Gaussian process models. These are sort of cherry-picked and not exhaustive, but I think these are sort of a good read. This is information on Gaussian process models. This is an interesting paper. These guys used inference networks way back in 2006, before they were, before things like the variational autoencoder had been developed. This is the link to the automatic statistician website. The papers on the data efficient reinforcement learning and the connections between GPs and neural networks. Thank you very much for your time, and if you have any questions, please take them.